Welcome to our discussion on the language of functions, or basically the basics of functions. In this video, we're just going to learn what a function is, how to describe it with notation, and what its domain and range are. So the central idea in understanding a broader sense of mathematics in the world around us is really to understand how functions work, because in general, a function is just some sort of mathematical expression or process that relates two or more quantities to one another. And this relationship allows us to represent many, many unknown amounts of one quantity with known amounts of another. And it allows us to model a lot of things that happen in the real world. So it's essential that you understand how a function works because they are used so often. So for instance, what would the graph of the number of sweaters sold at a department store from January 1st until March 31st look like? Well, wouldn't you expect it to decrease from left to right? As you move from left to right, the amount sold is going to go down because people are going to buy less and less sweaters as the weather gets warmer. Unless, of course, you're in the southern hemisphere, then that question would kind of reverse. But anyhow, a function is a mathematical equation that describes the relationship between the dependent and independent variables for a given situation. What the heck does that mean? Okay, dependent and independent variables. The independent variables are the input, the stuff you pour into the function, and the dependent variables are things that come out of a function. I like to use the example of a meat grinder because just about everybody's familiar with what a meat grinder is, right? You throw beef into a meat grinder and you turn the handle and it spits out hamburger, right? So the independent variable was beef, the dependent variable, right, the output was hamburger. Now you come back and instead you throw pork in there and you turn the handle and it spits out pork sausage, right? And then you throw foot, snout, hooves, all the junk and turn the handle and it spits out a hot dog, right? And if you go and put beef in it again, it's going to spit out hamburger. That's the beautiful part. That's what really makes a function, is that if you put the same input, right, if you put the same independent variable stuff in time and time again, you'll always get the same answer out. Now you can get the same answer for different inputs, but you can't get different answers for the same input, right? So the independent variable is the input and the dependent variable is what you get out of it. Usually when we graph things, the independent variable is the x, the dependent is the y. Okay, the dependent variable change with respect to the value of the independent variable. No duh, because that's what it does. It depends on the independent, right? So the dependent variable is the thing that is being changed by the independent variable, whereas the independent variable is allowed to roam free and be whatever it wants to be. Here are some simple examples, right? X is obviously our input, that's our independent variable, and then our output we would call y, but in this case, instead of y, we start calling them f of x. It's a function in terms of x, or we call it g of x. You know, the letter here doesn't really matter. What matters is this letter here. Inside the parentheses is an x, means this function is in terms of x, meaning anytime we see an x, that's the independent variable. That's the thing that we can plug a number into. And the reason why that's important is you could have a function with other letters in it, and those other letters could be variables, but they could also just be constants that are unknown, like a g for gravity. It's not really unknown, but we have to plug in the value for gravity before we move on with the function, because the gravity can change depending on, you know, if we're doing this on the surface of the Earth or if we're doing it on the moon and that kind of thing. All right, so obviously if we want to do f of 5, we just plug 5 in here and we get 10 minus 5, the answer is 5. Plug in 0, we get negative 4. Plug in negative 3 here, we get 9 plus 6 minus 5, and we get 10. That's all there is to it. They're nice and simple. Now the functions can get more complex, but the idea is still the same. Whatever is inside the parentheses, that's the input, and you're going to put it in for the variable they tell you. And if the variable is in more than one place, then you put it in for each place. And then you just do the right math operations, right? You got to remember your order of operations. First you do things inside the parentheses, then you raise things to powers, then you multiply and divide, then you add and subtract. All right, so pause the video and see if you can figure these ones out. Hopefully you got all the correct answers. Okay, the domain of the function are all of the allowed input variables, all the things that we will allow you to put into the function. And in general, you start with all numbers. All functions start off with a domain of all real numbers. That means all the negatives, all the positives, all fractions, decimals, square roots, everything. Every number you can think of, the entire number line in both directions. And then we start to restrict those numbers based on the function that we're using. And there are really only two things that make us restrict the domain, because there are only two things we can't do in math. We cannot ever divide by 0. That's not defined. It doesn't make sense. So if you have a function that has any variables in the bottom of a fraction, you have to make sure that the bottom of that fraction is never equal to 0. So you can't plug anything into it that would make it 0. So for instance, if you had something as simple as the function f of x equals 3x plus 5, obviously there's no fraction there, so its domain can be everything. But if you now have the function 3 over x plus 5, this is a potential problem, and the domain, right, is going to be the set of all x's such that x does not equal 0. Right? That's one way of writing it, or you could just say, okay, negative infinity up to 0, union 0 to infinity. And we use round brackets because it can't include 0. There's a lot of different ways we can describe what the domain is, but basically it just can't be 0, right? What if we had something like this, where it was 3 over x plus 1 plus 5? Now, can x be 0? Yes, because if x is 0, we get 3 over 1. So what value can x not be? Well, in this case, x cannot equal negative 1, right? Because then negative 1 plus 1 would give us 0. So that's the first problem we have, is we can't divide by 0. The only other issue we ever have that restricts our domain is we cannot take even roots of negative numbers. So you can't take a square root or a fourth root or a sixth root, right? Any even-powered root of a negative number. You can take odd, right? So you can take a cube root, right? A 3. We can take a cube root of negative 1, because negative 1 times negative 1 times negative 1 does in fact equal negative 1. So the cube root of negative 1 is just negative 1. We can do that. But you can't take the square root of negative 1. You get an I, which is an imaginary number, right? And you can't take a fourth root of negative 1, or any negative number, right? So those are the only two things you have to worry about. Whenever you have functions with variables in the bottom of fractions, you have to make sure you set the bottom equal to 0 and solve, and then whatever that value is, pull it out of the domain, right? If you take x plus 1, set it equal to 0, you move the 1 over, you get x equals negative 1, and then you go, nope, cross it out. It just can't be that. And then if you have even powered radicals, you have to also set that even powered radical to greater than or equal to 0. So a real simple example, and we'll do more later, but if you had f of x equals 3x plus 5. Let's say you had that. Well, you have to make sure that whatever's under the radical is always greater than or equal to 0. So that's all you do, is you set 3x plus 5 greater than or equal to 0 and solve, right? You move the 5 over, 3x has to be greater than or equal to negative 5. Divide by 3 and you get x is greater than or equal to negative 5 thirds. And that's your domain, right? X just has to be negative 5 thirds or bigger. Okay, so those are the only two things you have to worry about for domains. The range of the function is the set of all output values, so everything that the answer is allowed to be. Now, when you take square roots, because everything in here has to be 0 or above, when you take a square root, the answer is always going to be 0 or above. So the range of even-powered radicals is always 0 and above. The range of what we call rational functions, these things with fractions, are always going to be all real numbers, because as you get closer and closer to this what we call a point of discontinuity, this point of problem. So if we get, for this one, if we get closer and closer to 0, this thing, right, 3 is being divided by smaller and smaller things. And when you're dividing by smaller and smaller things, you get bigger. So what's going to happen is this thing is going to explode to infinity and negative infinity. So if this is a positive, a really, really small positive number, it goes to positive infinity. If it's a really, really small negative number, it goes to negative infinity. And then other functions will do other things. Obviously, a straight line will go as tall as you want and as small as you want. You'll have parabolas, right? Quadratics, things that look like horseshoes. And obviously, this is as low as it goes, but it goes all the way to infinity. So its range is going to be, let's say this is -2. Its range is going to be from -2 to infinity. But if you had one that was upside down, right, and let's say this hits right at 0, then its range is going to be from negative infinity up to 0. It all depends on what the function is as to what your range is. There's really no hard, fast rule about the range. It all comes from the function. And certain functions have certain types of ranges, and you'll see there are families of functions, right? Like all straight lines, unless they're horizontal, have a range of all numbers. And then all simple quadratics have a range that goes from a number up to infinity or from negative infinity up to a number. It just depends on if it opens up or opens down. Things like that. All right, let's try to make some sense of these mathematical relationships, i.e., let's figure out how we can work with functions when faced with functions. Whenever you come across a function, we use the more general term relationship because something can be a relationship without being a function. Because remember, a function, as I said, has to have that stipulation that every time you put a value into it, it gives you one and only one answer out. And those are actually, I shouldn't say rare, but they're special cases. You can have relationships that aren't necessarily functions. And you've probably heard of, the vertical line test to determine if something is a function. For instance, something as simple as a circle. That is not a function. It fails the vertical line test. But it definitely is a relationship. And there is a strong relationship between x and y. So we're just going to use the general term relationship to know that when we're talking about functions, we could also be talking about things that aren't necessarily functions. They're actually just relationships because they fail the vertical line test. But they still have all the other attributes, right? They still have domains, they still have ranges. There's still a relationship between the independent and dependent variables. And when we're dealing with those things, the first thing we need to determine is what is the relationship between that independent and dependent variable. More precisely, when we do something to the independent, what does it do to the dependent? And if we're given the algebraic representation of this relationship, with bunches of x's and y's, then we know what's happening. But if not, if we're given a picture, then we got to figure it out from the picture. We should determine the domain and the range of the function or relationship, right? And if we have a picture, that's pretty easy to figure it out. If we have the algebraic stuff, then if we know what kind of function it is, that helps. Otherwise, you can graph it. Different things to help you, but you want to figure that out. And then you want to graph it so you can get a picture of what's going on. So it all depends on how the information is presented to you, but you should understand the relationship between the input and output, figure out the domain and range, and figure out a picture. All right, so let's look at this example. The Print Perfect t-shirt company charges $200 to set up the design of the shirts and then charges $12 per shirt purchased. And if you were a baseball team or some other organization that wanted to purchase shirts for your team or organization, you'd have to figure out how much it's going to cost you based on this function, this relationship. So we could write a function to represent the relationship between the number of shirts purchased and the total cost. And hopefully you can see that it's fairly easy to figure out that the cost is going to equal $200 plus $12 times however many shirts you want. It's that simple. Now, the domain and range of the function. Well, if we're looking at this function in a general sense, if we're just looking at y equals 12x plus 200. What is that going to be when we graph it? Well, it's going to be a straight line, right, with a slope of 12. So from a mathematical standpoint, what's the domain of this function? And hopefully you're thinking, well, all numbers. And then what's the range of this function? Again, all numbers. But what if we're looking at this function in the context that we're given, right? So instead of thinking this is just y equals this, we're now saying this is a cost equation in terms of x. Okay, it still gives us the same picture, but we're giving it a different context. We're not just saying it's y, it's now a cost function. Now, is the domain still all real numbers? And hopefully you're all saying no, because the input variable is x, and x represents the number of shirts purchased. Can you purchase -3 shirts? No. Can you purchase -1/2? No. In fact, can you purchase 3.5 shirts? No. So not only is the domain, it can't be negative, it also can't be fractions, right? It's only going to be whole numbers, integers. Could it be 0? Yeah, absolutely. You could purchase no shirts if you wanted to, right? It'd be kind of silly, right? Because you're paying them $200 for nothing. But technically, I would say the domain is x is greater than or equal to 0, and it's only integers. And we can talk about how to list that mathematically later. What about the range? What's the smallest value this function could be? Well, obviously the smallest x is 0, and at that point you're paying 200 bucks. And then what's the largest it can be? Well, if x can get as big as you want, you're just going to keep adding $12 and $12 and $12 for each new shirt. So the range is going to go up to infinity. And then what about graphing the function? Well, we already said that it's going to look like a line, right? So that's what our line should look like. It should start at x equals 0 and y equals 200 and have a slope of 12. Okay, so when we're dealing with functions, remember, the key is you got to put it back in context. Yes, I know that 12x plus 200 is a straight line, and that straight line technically goes on and on forever to the left and goes as low as you need as well. But in the context of this question, it's no longer y equals 12x plus 200, it's f of x equals 12x plus 200. And that's a function that refers to something in the real world. You can't buy negative shirts, and therefore you get a different answer. All right, hope that helps.